My name is Keith Basil. I want to thank you for attending this session. OpenStack's a pretty hot topic nowadays. I am the principal product manager for OpenStack for Red Hat. Just want to warn you guys, this session will be recorded. Slides will be available later this week, I think around Friday. I need to apologize. This session was listed in the agenda as a 1. I did a rehearsal to some folks at Red Hat. They said it's a 2. So it's a little more technical than the session for Jerry and Chuck this morning, the marketing folks. So I'm somewhere in between a marketing guy and the hardcore engineer guys who are over here on the right. So they've been making fun of me already. So 2-bar session. We'll get started, jump right in. There's some seats up front if you guys want to come in. So a little bit about me before we get started. I'm what you call a Virginia hair scrambler. Basically, I race dirt bikes in the woods with a bunch of other crazy folks on weekends, kind of weekend warrior thing. I play chess. I teach chess at the local university to middle school kids. Professional life, obviously I work at Red Hat. Before Red Hat, I was with Cloud Scaling. Before that, Time Warner Cable. I see some of my federalcloud.com compadres in the room. So I did some cloud architecture for the public sector. Worked at Cisco, worked for a few startups. Blended, I go by No Sleep, so I'm on NOSLZZP, internally at Red Hat, Skype, Twitter, GitHub, et cetera. So we'll walk through this agenda here. So there's 4 parts to this talk. What I want you to walk away with, a few things here. I want you to truly understand what OpenStack does well. That's number 1. Number 2, I want you to understand which applications run well on OpenStack, okay? And I want you to have some beginning insight into what I call elastic cloud concepts. A lot of folks have been talking about the elastic cloud, but I think after this talk, you'll have a true appreciation for what you need to start thinking about in terms of elasticity. And then for you guys who are on the more technical extreme, if you're really thinking about deploying OpenStack, especially in production, I'll give you a few questions and insights into what you need to consider for production-grade OpenStack. Okay, so what is OpenStack? Real quick, it's software, and it's a community. And I'm going to talk about those real quick. It's an open source software platform for building infrastructure, cloud infrastructure. As a community, it provides formal governance, and there's a large body of contributors to OpenStack, and we'll talk about the constituents in a second. So what problem does OpenStack solve? Well, as a framework for elastic cloud infrastructure, it allows you to manage compute, network, and storage. It basically provides a natural infrastructure for elastic applications. We will talk in great detail about elastic applications in a bit. So the component detail, let's a little bit further. There's compute, networking, and storage. Basically, compute gives you virtual machine management, the complete lifecycle of the virtual machine. It has comprehensive hypervisor support, ESX, KVM, LXC, et cetera. We'll go into that. On the network side, it is IP address management, provides security services in terms of security groups, very similar to AWS. Storage, you have both block storage, which are volumes, and object storage, which is similar to S3 on AWS. So as a community, there are 3 constituent groups. The tech community committee, basically the tech guys, they define the strategy and direction of where the software is heading. The board of directors is basically the shepherd for the organization. They protect the name, they promote, et cetera. From the OpenStack bylaws, the OpenStack project has been defined as a set of core projects, core OpenStack projects, with some auxiliary projects backing that up, library projects, gating projects, supporting projects, et cetera. The foundation as a whole has attracted more than 7,000 individuals from 100 countries, 850 different organizations, and has secured over $10 million in funding. A large chunk of that came from the platinum level sponsorships, of which Red Hat is one of 8 platinum foundational members of OpenStack. Okay, so a little bit about the history of OpenStack, and I won't spend too much time here because I know you guys, I get a sense that you guys want to get more into the technical side of it. So the takeaways here is that in the beginning, there was Rackspace and NASA. Rackspace had a fairly mature object storage service. NASA had a fairly mature compute storage service. They came together and decided to create OpenStack. If you look on the screen, you'll see on the left that the naming convention follows the alphabet. So we started out in Austin, Bear, Cactus, et cetera. And we settled into a 6-month cadence in terms of development cycles. So at each level of release, the components inside OpenStack have matured greatly. So you can see that first production-ready OpenStack was when Diablo was released. We're working on the H release now in terms of code work. The names are chosen by the cities or counties that near the summit where it's held. But over lunch today, I found out that that convention has been dropped. So the next release after Havana is going to be called Ice House. And the reason, I don't know why the reason Ice House, but it is what it is. The vote ended last week. So let's talk about the trends and growth. Red Hat assigned its first developer to OpenStack just before Diablo. That was Mark McLaughlin. He's principal software engineer at Red Hat. He lives in Ireland. He did the talk on OpenStack at the last summit. Essex was the first OpenStack release with Red Hat code. And there's some important bubbles on the right-hand side there. The bubbles represent the size of the committers across the top 10 organizations. So top 10 organizations being Red Hat, IBM, Rackspace, et cetera. So if you look across the top 10 of those folks, you'll see that in Essex, we had 47 individual committers. And then it has grown from there to 71 and to 230 committers for Grizzly. The last OpenStack summit was in Beaverton, Oregon, and it had over 2,400 attendees. And our next summit later this year in November will be in Hong Kong. It's the first summit outside of the US. Okay, so as far as Red Hat goes, we love open source. The first release with Red Hat code in it was Essex. And when you wrote up all the commits to OpenStack, we came out as the #3 contributor to the project. With Folsom, we were #2. That was 6 months later. And 6 months later after that, we were #1 for Grizzly. Okay, thank you guys. So basically, Red Hat folks, we naturally gravitate toward open source. I mean, there were folks at Red Hat who were contributing to open source without even being assigned to OpenStack. Okay, so it's just the way Red Hat operates. And this is a shout out to some of the folks in the room here. Shown here are some of the more suspicious of the more than 40 folks who have contributed to Red Hat OpenStack. And for Grizzly, if you take the top 10 individual contributors for the project, 5 of those are Red Hat employees, and a few of them in the room here. Okay? So what does that mean for Red Hat customers? Basically, it means the following. It's a direct value that can be summed up like this. When there's a support issue for Red Hat OpenStack, it's really nice to have the guys who shepherd, write, maintain, bug fix the code right there in-house to be able to answer that question. So it's a good fit for us. Okay, so we're going to jump into the architectural components of OpenStack. So you've probably seen this before from the marketing talk at a high level. OpenStack has individual components that are modular in nature. So there's a core set of services, so you'll see on the left Nova, and we'll go through each one of these in a little more detail. But the takeaway here is that OpenStack has been designed for horizontal scalability and elasticity. Elasticity meaning that if you see a increase in requirements for your cloud, you can just rack and stack and continue moving on in terms of expanding your cloud. So some of the basic design tenets of OpenStack features, obviously they feature scalability and elasticity, but those, I have to emphasize, are the main goals of any core project in OpenStack. So what does that mean? That means that if there's a new project that's introduced into OpenStack, it should hit upon those design goals from an architectural point of view. This is the beginning of your understanding of the elastic cloud. Okay, this is very different from traditional enterprise virtualization, which we'll go into. So the components must be horizontally scalable. So for example, if we run out of compute services, we should be able to just rack up more compute services, be it the scheduler, the compute nodes, what have you. So it tries to take a shared nothing approach so that there's no huge, what I call failure domain. So there's no big sand behind OpenStack that can fail and take your entire cloud down. So the failure domains are very small, it's modular driven, et cetera. So we'll go into each one of these components in more detail. Okay, so the first one is the dashboard. This is pretty straightforward. If anybody's had any experience with a hosting company, think of this as your control panel. So the dashboard is where you would log into OpenStack. You would see what resources were allocated to you in terms of quota. You can spin up a virtual machine. You can create a volume. You can attach that volume to a virtual machine. So this is the GUI to OpenStack Horizon. Pretty straightforward. The next piece is Nova. Nova is responsible for all the compute services within OpenStack. So Nova supports multiple hypervisors. KVM is by far the leading hypervisor of choice in terms of production deployments. KVM has roughly about a 70% market share for OpenStack. There's Zen, which has some legacy code there, and Linux containers, LXC. In your spare time, do a Google search on the hypervisor support matrix, and you will see a breakdown of all the hypervisors that are supported, and you'll see which of the Nova API commands are fully supported by a particular hypervisor. Just because you see Hyper-V and ESX and LXC on the screen doesn't mean that there's full API support for those hypervisors, okay? Nova provides two APIs, the native OpenStack API, which is an open API, and then there's also a hook for a subset of EC2 compatibility. So if there are folks in your organization today who have DevOps tool sets that are speaking to EC2 in terms of provisioning to Amazon, you could easily point them to an in-house version of OpenStack using the EC2 API for compute. So Nova does scheduling. So when a virtual machine instance request comes in, and we'll walk through the flow, Nova decides what compute host to put that on, and then there's a separate component of Nova that actually runs on the hypervisor that actually does the heavy lifting in terms of requesting services and such. So next up is block storage. This is codenamed Cinder. So let me back up, and actually I don't have to back up, but if you look at the top is the public-facing name for the service. So you'll see block storage, so OpenStack block storage, and then OpenStack compute. Well, there's code names for each one of those. So for compute, the code name is Nova. For block storage, the code name is Cinder. So Cinder has, like other OpenStack components, comes from actually has a plugin-based model. So it's a framework where, for example, if NetApp wants to plug its service architecture into Cinder, then NetApp would provide an open source driver. It doesn't have to be open source, but they would provide a driver for Cinder so that Cinder could deploy and request volumes on the NetApp hardware, okay? Same thing with EMC, LVM, with Linux, if you want to use commodity hardware. IBM's, I think XIV's storage system has plugins for this. So you can look at Cinder and see which vendors out there support Cinder from a driver point of view. Each one may, just like the hypervisor support, each one may not support full API functionality as described by OpenStack. So next up is networking, codenamed Quantum. So Quantum's name will go away because of legality issues. There's a company out there that is claiming copyright status on the name Quantum. So that will change, or it would just be called OpenStack networking going forward. But Quantum is the beginning of the software-defined cloud for OpenStack. So basically, it gives you the same plugin model where you can have network vendors, hardware, et cetera, software, where Quantum as the capstone of the framework would then talk to the various plugin providers to spin up, or manage IP addresses, create L2 over L3, layer 2 over layer 3 networking models. Things like QoS and security groups are handled by Quantum. So any networking requirement within your virtual machine environment. Quantum is the guy that's doing the policing for that. Okay? So next up is Glance. This is the image service. Now this is pretty funny. When I first got into OpenStack, I looked at Glance as the image service and I said, why would I need a service to serve up JPEGs and PNG files and such? Like, there's a lot of guys working on this. I say, this is really not that hard. So I say that to say that, look, everybody's beginning and kind of new to OpenStack, and don't be afraid to ask any silly questions because I've been there. So it's more than that. So Glance images are disk images, okay? They're not, graphical files. So it supports raw disk images, QCal, you see on the screen there, ISOs. And it's kind of it's a catalog. So when you have a request for a particular image, Glance says, hey, I know about that image, and here's where it is. It's that simple. And it is responsible for storage for those images as well, okay? And we'll see Glance come up in a minute. So next up is the object storage piece. This is codenamed Swift. Object storage is basically, if anybody's here used Amazon S3, it's basically S3, open source version of S3. There's an API where you HTTP upload a file, so you have puts, you have gets. Very basic. It's for static objects. So if you have on your laptop, maybe you have a library of MP3s or videos, you can then just put those up into the cloud and know that they're replicated to some degree. It natively out of the box supports 3 replications, but that's a tunable. Very, very simple service. And finally, we have Keystone. So Keystone is basically the traffic cop for OpenStack and the components within OpenStack. So it's responsible for authorization in terms of if a request comes through, Keystone will grant a token that's time limited for that particular action based on the credentials and the roles. It manages the catalog, service catalog, the endpoint definitions, and the security policies for how you set up your cloud. There's some pluggable backends that you can embrace. I think we're working on finalizing the Active Directory support for Keystone. So it's the traffic cop for OpenStack. Okay, I took this slide out, but I figured this was a 2, so I left it in. The way OpenStack components talk to each other is basically with what's called a message queue. There's a couple of queues that we support on the back end, most notably Rabbit and Cupid and 0MQ. So if the request for a virtual machine comes out, basically it gets put on the wire, so to speak, and then the compute nodes will listen to what they're supposed to do, and it's all via the queue. Okay, there's 2 projects that I want to talk about that are destined to become core components of OpenStack. The first is Ceilometer. So what is a ceilometer? So if you Google the word ceilometer, you'll see that a ceilometer is a device that you put on the ground, and there's lasers that come up and bounce off the cloud cover to measure the height of clouds, okay? So in the context of OpenStack, Ceilometer as a project is used to measure usage data within the cloud. So if measure and store, so that when you want to do billing for cloud usage, you can bill by CPU usage, disk usage, et cetera. So Ceilometer is all about collecting stats. Some monitoring in terms of service. It's graduated recently from the incubation stage to what's called integrated. And I think the next stage after integrated is full acceptance as a core project. So we're getting there. Okay, the next one is Heat. This was actually introduced by a Red Hat employee, one of the Steves. I can't remember, is there Steve Hardy and another Steve? But basically, Heat gives you orchestration of your Elastic application. Not to go into too much detail here, but basically, you can describe your tiered application with a Heat template, upload that template into Heat, and Heat will automatically deploy your entire application. It's like the coolest thing. It also has triggers for scalability. So for example, if you see you can give Heat triggers where if you see traffic reach a certain level, you can have Heat automatically deploy additional virtual machines to handle that load. So there's the elasticity part of the template is there as well. So in the public sense, in terms of AWS, it's modeled after the CloudFormation service. And it's great as a tool to repatriate workloads from Amazon to your internal cloud on top of OpenStack. Okay? So let's actually walk through a request, and we'll see which components are touched by OpenStack for this request. So here I have a guy with a smiley face. He has logged into Horizon. He's been authorized. He's into the control panel. He clicks a few buttons. He says, hey, spin me up a virtual machine and make it large. Okay. The first thing Keystone does, it says, excuse me, do I know you? Okay, I need to see some papers. Okay. So he authenticates against Keystone. He's given a token, the equivalent of a one-day pass at King's Dominion, right? So he can ride all the rides, right? So now he's got his one-day pass, and he can do things. And we're going to continue with the request. So Nova, as the compute engine, looks at his request and says, OK, his papers are good. It's time to get to work. Let's go ahead and start spinning up this virtual machine. So Nova says, OK, we need to find a place to build this VM. What capacity do we have available in the cloud? So Nova then goes through the Nova scheduler, finds and identifies a machine, and says, OK, you're it. You're going to be the machine that we're going to spin up this virtual machine on. And then Nova, at this point, says to Quantum, hey, I need a network with all the trimmings. OK? Quantum then responds and says, here's your IP address, here's your default route, and oh, by the way, here's your firewall settings in terms of a security group for that virtual machine. The Nova component on the hypervisor then says, sender, do you have that volume? Is it ready? So it sends a message to the sender. And sender says, indeed I do. Don't forget to mount it. Okay? And this is where all the iSCSI traffic magic happens underneath the layers, right? So this is now, you have a virtual machine, you have an iSCSI connection, but you're not fully baked yet in terms of having a virtual machine ready. So then the compute node says, hey, Glance, I need a Rails 6 image. What do you got? Glance looks up in the catalog, says, OK, Rails 6 image, that's stored over there. But Glance then gets out of the way. There's no transmission through Glance. Glance passes the URI to Nova. Nova then fetches that image directly. So now, think about it. The machine has an image, network bits. It has a volume, and it knows from the instance type what size of machine to build. Okay? And now it's rendering time. So now Nova speaks to libvirt on the machine and says, hey, render this virtual machine, create this virtual machine for me. And then the machine gets built, and the customer says, thank you, OpenStack. Now he can log in to the machine with SSH, what have you. So that's the complete cycle at a very high level. There's a lot more detail to that, and Russell Bryant will have a more complete, more detailed talk about these components later. OK, so we're going to jump into the Elastic Cloud and the understanding of the Elastic Cloud. OK, if you can only take one thing away from this presentation, hopefully it will be the ability to understand the difference between an Elastic Cloud and enterprise virtualization. OK? You have to understand which workloads work best for each of those scenarios. And we're going to go into that right now. But this should be your main takeaway here if you don't get anything else about OpenStack. OK, so let's talk about this. The Elastic Cloud does not equal enterprise virtualization. They're two different worlds, two different philosophies, two different architectures. And I've taken the NIST definition, the National Institute of Standards and Technology. Their definition of cloud is self-service. That's important. If you have to fill out a form or submit a ticket and remedy to get a machine provisioned, that is not self-service. Okay? All right? Nate Burton from the National Security Agency did a talk at the OpenStack Summit, and he said that before they deployed OpenStack, they would have to fill out pages of documents justifying hardware to be provisioned for their projects. And he said by the time they got back with the approval, they forgot why they actually requested the hardware in the first place. Okay, so self-service is a huge piece. Network access means basically network access, so you can deploy this from anywhere as long as you have net connectivity. Rapid elasticity, so if your application needs to go from 10 virtual machines to 100 virtual machines, it should just be able to do that very quickly. And the final piece there is measured service. If we're not measuring the service in terms of bill back, charge back, accounting for the actual uses of the cloud, to me, that's the elastic side. And if you look at enterprise virtualization, and there's nothing wrong with enterprise virtualization. I mean, you might feel a sense of fanboy attitude for the elastic cloud because that's where I come from. But there's a place for enterprise virtualization. And the takeaway here is that enterprise virtualization is all about the hardware. You're packing virtual machines into the hardware. You're getting efficient usage out of the hardware. You have a minimum server count for the hardware. It has nothing to do with your application. It's all about the hardware and getting maximum use out of that. So please understand that. The workloads are evolving, okay? So traditionally, you would run a big application, big enterprise application, maybe Oracle, maybe Exchange Server, maybe SQL Server inside your organization, and it's a really large virtual machine, 128 gigs of RAM, 8 vCores, et cetera. They keep, okay? The applications have no awareness of the infrastructure. They just expect the infrastructure to work. What I call this gold-plated hardware, okay? So the enterprise virtualization, enterprise apps expect gold-plated hardware. And on the other side, with cloud, the applications expect the commodity hardware to fail, okay? So there's a different philosophy. The fault tolerance on the cloud side is built into the application layer, not the hardware, okay? So, yeah, we'll leave it at that. All right. So this is the famous pets versus cattle analogy. This was talked about briefly in the morning session. And this quickly illustrates the thinking behind the two models. So on a scale-up model, if you had Oracle running and you needed more RAM, you would just basically give the virtual machine more RAM. It's scale up, okay? So you treat that server like pet. I heard this dog answers to the name Ellison, okay? So you give the pet a name. So we love Ellison, okay? He's friendly. We got to have our mission critical apps are running there. If Ellison goes down, the company stops, everybody comes around. This is, okay, we got to get the server back up. Okay, there's an emotional attachment to the server, the pet, okay? All right. On the other side, servers are treated like cattle. This is the cloud elastic model, where they're not given names. They have number tags in the ear, okay? All right? If they get sick, you really don't care, okay? I mean, there's a more violent version of this analogy, but I just, okay? But I just put in here, if they get sick, you just get another one, okay? All right, I'll leave it at that. All right. So there's no emotional attachment to your herd, right? Okay, so think about your workload. Okay, is this a workload that is mission critical that I have to have up and running 100% of the time? Then yes, then it's a pet, okay? If you have an application that scales out and kind of flows, and we'll get to this, it's more of the cattle model where it's just standardized, commoditized hardware. I was, in fact, arguing with a guy inside Red Hat. He's like, we need to run RAID 10 on the machine for performance. Like, dude, he was arguing with me the fact that RAID 6 takes a long time to rebuild. I said, if the RAID array crashes, pull the machine out of the rack, put another one in. I'm not waiting for anything to rebuild. I'm just going to reprovision the node and keep stepping. So it's a different philosophy, okay? Okay, so why is the elastic cloud needed? Okay, the two reasons why we need to have an elastic cloud. Our data is too large, okay? The amount of data that we're processing, the amount of requests that we're getting, it's too much for one computer or one small cluster of computers to handle. You need scale-out architecture to handle the flow of big data and large numbers. In the keynote this morning, I'm probably going to mess up his name, but Ram Apanaraju, he said there were like 5 devices for every person on the planet, okay? This is Facebook scale things. And granted, not everybody's building a Facebook level application, But there are specific use cases in the enterprise that fit this model where the data is just too large and there's too many requests, or you have both, okay? This is the driving requirement for Elastic Cloud, okay? Look at Netflix. 30 million users in the US, the UK, Latin America, Canada, multiple client options. I can get Netflix on my iPad. I can get Netflix on my iPhone, my Xbox, okay? My computer, okay? That's a large number of clients. And look at the data they're serving. They're streaming video. I used to work at Time Warner Cable, and we would complain that 70% of the cable internet traffic was going to Netflix, okay? It's amazing. So I'll come back to Netflix in 1 second. And one thing I picked up from the keynote yesterday was that this problem set is bigger than one company, okay? If you went to one company to solve this problem, maybe like VMware, first, I don't think they could do a good job of solving that problem. And then you'd be locked into that one vendor. So the beauty of OpenStack is that it's open source. And with that plugin model, the framework, you can plug in, let's say, EMC where it fits best. You can plug in 3PAR where it fits best. You can plug in Arista networking where it fits best. So it gives you a lot of choice to solve this problem. So the other takeaway here is that servers fail. The cattle die. You just need to deal with it, okay? Okay, so some people want to argue with me about this. So I did this math here, okay? So assume you had a mean time between failure of 30 years. A server that's going to stay running for 30 years. If you deploy 10,000 of those machines, you would watch one of those servers fail every day, okay? Every day. And this doesn't even account for the fuzzy stuff like 1 to 5% of your disks failing over the first year. It doesn't account for servers crashing in terms of the operating system, at least twice a year, or 2 to 4% failure rate. The takeaway here is that fault-tolerant software at scale is inevitable. This is where everything's going. This is why there's so much hype around OpenStack, okay? Because it gives us a tool set to solve this problem. So knowing that, I want to show you, I'm going to change the pets versus cattle analogy to something brand new here. I'm going to give you an example of elastic agility with scaled and small failure domains. So here's a school of fish. To me, this shows elasticity and agility. So check out the reaction times of the fish. So back to the big two problems, like a huge number of requests come in, how are you going to react to that? So your application should have that intelligence and be able to react to that pretty fast. This represents reliability and availability, okay? I'm not a biologist. I don't know why school fish do this. I don't know what the purpose is, but they're there to do it, okay? All right? And it represents small failure domains, meaning that if 1 or 2 fish get eaten by a shark, no big deal, okay? You've got fault tolerance built into your application, okay? And the takeaway here, which is awesome, is that the ocean gives you the appearance of infinite resources. Those fish could literally swim around the world and think that the ocean was going on forever, okay? It's the same thing with cloud. You look at Amazon, it's like, okay, Amazon's real big. I can actually spin up 10,000 servers and they would be able to handle it. But I know it's not infinite. There's some breaking point. This is the same model, okay? The school of fish here is your new elastic application. So I'm on a lot of calls with customers, and they have these legacy applications, and they ask the question, okay, but why can't I put my application on the cloud? And you can, from a pure technical level, you can run your enterprise applications on the cloud. But it takes a great deal of work in terms of modification. So how do you make an application that expects layer 2 connectivity with its neighbor to work in an environment that's 100% layer 3? The takeaway here is that, going back to the pets analogy, is that it's fairly unnatural. It's extremely unnatural to expect an enterprise application to run in the Elastic Cloud or in the water. So yes, pets can go in the water. You can run Oracle and Exchange on Amazon or in your OpenStack cloud, but the performance envelope is probably not going to be acceptable for your users. Why is my email slow? Why is the database slow? Okay, it's just a different world. So I've got to give you a warning. What you're about to see is a pet doing an unnatural act. Okay, but everything is okay in the end. And unnatural acts can be very impressive. So this is a golden retriever that's been trained to dive. This is a marine salvage dog. Who ever heard of such? Okay? So the question and takeaway here is, can you train your dog, your application, to do this? Where do you start? Do you look in the yellow pages? Okay, marine salvage training dog. Okay. Okay. How long did it take to train this dog? Okay. How long will it take to shoehorn your application into the Elastic Cloud? What does the dog think? Okay. The real question here, all kidding aside, the real question here is, does this model scale? Okay. We have some financial customers where they have 9,000 enterprise applications. 9,000. Okay. Okay, that's not going to scale. So anyway, the question here is, yes, enterprise applications can work, pets can swim, okay, but it's not natural for them, and they won't perform very well. And there's a lot of effort to take an enterprise application, put it on elastic infrastructure, and expect the same performance envelope, okay? It's a serious commitment to time and resources, and there's better ways to do that. And one of the best ways to do that is just have two clouds. If you're running VMware or Red Hat Enterprise Virtualization in your organization, don't touch that. Leave it. It's fine. There's going to be applications that require that for the next 10, 15, 20 years. But when you start new with the Elastic world, just spin up a greenfield deployment of OpenStack and use something like CloudForms, which is a Red Hat product that can see into both. So there's a single pane of glass for managing both enterprise loads and Elastic loads. Okay, so let's talk about OpenStack in the real world. So OpenStack is increasing in maturity. We talked about the 6-month cadence. Again, unfortunately, because organizations are struggling with the Elastic Cloud concept, people are whiteboarding Franken clouds every day where they're trying to bridge the two, okay? I'm not saying those efforts are totally wasted, but what happens is, by trying to make this Franken cloud, you come up with something that's insanely complex. You spend a lot of money. It's like it's training the dog. You're training the dog to dive, okay? It's just, it's not a good strategy. There are greenfield deployments, like I said earlier, where you should just think about a dual cloud, the tale of two clouds, in terms of the application, the enterprise applications and the Elastic applications. People are looking for guidance. So there are some pet-friendly strategies, but I think it's not so much a blending of the two philosophies as it is modifying your enterprise application to some degree, and then maybe doing a smarter approach to your Elastic Cloud, and then maybe it can work. But there are some pet-friendly strategies underway. So knowledge is being built around deployments every day. There was the OpenStack Operations Guide. This is a free book that you can download. What happened here was, I think 8 people got together in Texas in a room, and these guys had real-world operations experience. They did what's called a book sprint. They wrote a book in 5 days, and they called it the OpenStack Operations Guide. So you can Google for that, download the PDF, start reading it on your way when you leave the summit. The OpenStack Security Guide, this is a work in progress. There are 15 to 16 guys who have deep security experience with OpenStack and or in the federal space. Some guys from the National Security Agency, some guys from Red Hat, and other OpenStack vendors. The plan is to get together in a room last week of June, 5 days, and write the first ever OpenStack security guide in terms of best practices and deployments and reference architectures, et cetera. So it's maturing. So 2 questions that we get all the time. What does the network look like? What does the hardware look like? On the network side, the 90s called, they want their network architecture back, okay? Things have progressed much further, and we're gonna look at each one of these questions in more detail. Amazon and Google have figured it out, so we're gonna embrace and extend the approach that they use for the Elastic Cloud in terms of the hardware. So let's talk about the network. So this represents kind of a heat map of your services within the cloud. Each box, you can just pick a reference. You know, the lighter squares could be compute nodes. The darker squares could be block storage nodes. And the thing that we're trying to solve for here is what I call equidistance between the nodes. So no matter how big the cloud is, you need to make sure that there's very fast and consistent connections between each one of these blocks, no matter where they are in this map, okay? That gives us scalability and gives us performance, okay? So we need to make sure that this node can talk to this node, okay, with the same rough characteristics and performance as something fairly local. So your cloud's going to grow, okay? If you don't have a network fabric that can meet the requirements of an elastic cloud, you could be in trouble really fast. Each one of these blocks, as we grow, it could be one server, or it could be a rack of servers. So your network fabric should support this kind of growth model and ensure that the network I/O requirements are consistent through the entire fabric. So if the black squares here were block storage, they would have what I called a different upstream or subscription ratio into the fabric, because you want to make sure that they're streaming out as much iSCSI traffic as they can to everything else in the cloud. So you can do performance-based mapping within your map there. Because of all the squares, it takes a while for this thing to flip. They're individual objects. I need some cloud power. Come on. There we go. Okay, so we're growing again. So is this, I did the math, is this 1,152 servers? Or is it 1,152 racks with 16 servers each, which is 18,432 servers? Can your network handle that? Well, the answer to the question is, it shouldn't matter if you've built your fabric right, okay? So a spine and leaf network topology, you guys should probably explore that. Ask your friendly network vendor. There are reference architectures out there today. Juniper, Dell, Arista, Dell being Force 10, Cisco. These guys have all figured this out. Okay? There's extremely high port density now, 10 gig E, non-blocking I/O. Layer 2 over layer 3 works very well, so you can mimic a VLAN on top of a layer 3 model. Excellent stuff here. Okay, so let's talk about the hardware. So we have to examine what the public guys are doing first. I got to give you a little bit of background before we get into specifics. So on the left here is Google. This is Google's new compute class for standard compute. And the takeaway here is that Google and Amazon build their instance classes based on this model. So they have a large instance, right, which has a certain number of resources in it. The next one down is 1/2 of the previous. The next one down is 1/2 of the previous. So extra large, large, medium, small. So small is basically 1/8 of the large. Again, we'll get into why that's important here. So we call this fractional proportions. So the ones below are a fractional proportion of the big guy. And collectively, this is what we call an instance class. And the takeaway here is that we build hardware to match this, okay? And I'll show you why. So if we solve for the biggest guy, we automatically get all of the smaller guys, okay? So if this particular machine here, I've got some specs here, if this is the M1 class of hardware with 128 gigs of RAM, 16 1 terabyte disks, and 2 processors, then we can pack in 4 of the extra large virtual machines if we use looking at the Amazon model. And the reason we want to possibly model Amazon and Google is because if you have workloads already out there in the public cloud and you want to bring them in-house, you want to make sure that the performance envelope matches when you bring that workload in-house. So this is a great way to get the same kind of performance characteristics from your hardware. The next takeaway here is that with the Elastic Cloud, there's an implicit contract between you as a cloud operator and your tenants within the cloud. Okay, so I'm an application developer now. If I'm deploying virtual machines on your cloud, I know that the performance of a medium should be what you tell me it is. And no matter how many mediums I spin up, there should be a consistent performance envelope across the board. Because if I don't have that consistency, how can I build an elastic application? It's almost contrary. It's the same model as if you're going to build a house, you would not have random cinder block sizes or brick sizes. You have to start with a basic unit that's going to be consistent throughout your entire cloud. This also ties back into the network performance, so that the network performance, no matter how big it is, will be the same and consistent. So the guarantee, the implicit contract between you and your tenant remains as constant as possible. This is a compute node, conceptually, with very efficient bin packing of the virtual machines. So if you look at the extra large machines, that's basically half of the machine. Okay? If you go look at the Amazon definitions of a class, they'll tell you that an extra large virtual machine has a much higher I/O performance envelope than the small ones. If you look at the machine, we've got 4 extra large virtual machines grabbing 16 spindles. So whatever the I/O capacity of those spindles are, you're basically allocating 50% of that to the virtual machines that are largest. If you had this machine full of smalls, they'd all get roughly 1/64th of that I/O from those disk spindles. So you are enforcing the you're enforcing the service level for that particular virtual machine. Okay? So this machine, if you look at the Google model, basically gives you 4 of the big guys, and on Amazon it gives you 8. And this is a picture of a potential Amazon class of hardware. So out of the box, this tells you a few things. I need 128 gigs of RAM to be very efficient. 16 terabytes gives me a good I/O performance ratio per VM. And the second thing it tells you is that I can have a maximum of 64 virtual machines on this hardware. That means I need to have 64 IP addresses allocated to that one node. If I've got 16 nodes in a machine, just do the math. Then you can start planning for how many elastic IPs you need to map down into your cloud from the egress side. Okay? So it all works together holistically. And to summarize that, you look at your network fabric, which we talked about. You look at the compute and storage parameters and profile. And then OpenStack is the glue that ties this together. Because if I have a rack of M1 class hardware, I can tell the scheduler that says when a request for an M1 virtual machine comes in, around the circle that we said, when the request comes in, send that request and schedule it on a hardware node that matches this performance characteristic. So it binds everything together. Okay? This is where OpenStack fits. This is the elastic cloud model. And in the middle is the service level or the implicit contract that you're making as a provider to the folks that are consuming your cloud. And this could be 100% internal. You still want to have some stable, repeatable SLA on a per VM basis for your internal customers as well. Okay, I'm going to go through a few deployment profiles real briefly. PayPal is adopting OpenStack, lots of users. They have a do-it-yourself team leveraging OpenStack. We're working with PayPal, and some of our friends are working with them as well. They've identified a few silos of compute or resources that they're going to convert to the elastic cloud. Our friends over at CERN, Tim Bell, they're ramping up to 15,000 hypervisor nodes with 300,000 VM possibility by the end of 2015. The National Security Agency, we need somewhere to store all the data. Big data here is truly big. No, but we love the NSA. They're a huge Red Hat. They have good experience with OpenStack. Nate Burton said that they've been working with OpenStack since Cactus, so that's a long time to be using the cloud with an elastic cloud. So in summary, OpenStack is a software and it's a framework, a very large, diverse, and passionate community, has a very fast cadence. Everything is maturing very fast. And again, the takeaway here is that OpenStack provides a natural affinity for elastic applications. The deployments, though, are not what you would see in the 90s. You have to upgrade your thinking and get fresh thinking in terms of having a network fabric to support the elastic cloud. And it's actually deployed at scale today. Lots of folks are using OpenStack, but the use case has got to be spot on. And finally, before joining Red Hat, I was with a couple of startups in the OpenStack world, and I would be on sales calls, and we would say, yeah, we're going to be the Red Hat of OpenStack. Okay? And so starting early in Essex, it's when we got started, Red Hat got started, and just want to let everybody know that Red Hat intends to be the Red Hat of OpenStack. So thank you very much. It's been a privilege to be able to present here. Please check out some of the other sessions.